Hello, everyone. Once again, thank you so much for your time. Today, I'd like to continue on our discussion on analog modulation. Our topic for today's discussion is on modulation index, which is also denoted as M. We are going to see how does the modulation index affect the amplitude modulation. This will be the part 4 series discussion on amplitude modulation. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe button. Please also turn on the notification bell in order to receive more information from this channel. Thank you so much. Let's define what is modulation index. In amplitude modulation, the depth in which the amplitude of the carrier is being changed by the modulating signal is defined as the modulation index M. And typically, it is actually expressed as a percentage. Okay, so this is a formula to calculate the modulation index. M is equals to peak amplitude of the modulating signal over the peak amplitude of the carrier signal. Okay, like what I mentioned, typically it is normally expressed as a percentage. Today, our objective is how can we derive this modulation index formula. So I'm going to show it to you step by step. How can I derive this formula? Okay, there are a few key parameters that you should take note. Okay, Vmax, okay, is basically the maximum possible. So this is called Vmax. Vmin, okay, you can see from here, okay, is at the lowest possible level of the modulating signal. So it's defined as Vmin. Okay, and then if you know that the modulating signal actually appeared at the envelope of the modulated signal, therefore this part here is EM, okay, which is the peak amplitude of the modulating signal. And then last but not least, we know that this is actually the peak value of the carrier. Okay, so these are the 4 important parameters, okay, that we're going to take a look. We also have the frequency. Okay, we have the frequency of the carrier and also the frequency of the modulating signal. Firstly, let me define how can we derive this equation. Okay, EM is equal to half Vmax minus Vmin. Okay, so take a look over here. There are 2 important lines that I have drawn in red. Okay, firstly, can you see that how I can calculate the interval between the 2 red lines? If I do a Vmax minus my Vmin, I actually get the interval between the 2 red lines. And from this diagram here, you can see that if I do a divide by 2, I actually can get my EM. So this is how I obtain this equation. Okay, in order to get the EM, what I need to do is I use Vmax minus Vmin. After that, I do a divide by 2 since they are symmetric, and hence this is how I obtain the EM. EC, okay, again, I have drawn 2 red lines that is essential for us to do the analytics on this diagram. Okay, now I need to find what is EC. Okay, take a look over here. So from here, you can see that if I use Vmax minus EM, I will actually get EC, correct? So this is how I'm going to approach. So what I need to do is EC is equal to Vmax minus EM. Okay, so this is the formula that I need to prove. This is what I told you earlier on. Okay, I know my value of EM, which is half Vmax minus Vmin. Okay, so from here, I know that Vmax minus half, I have half Vmax. Minus minus become positive Vmin. So EC is equal to half Vmax plus Vmin, okay, which is illustrated here. Okay, remember our objective is to get the modulation index. Okay, earlier on, I have defined that modulation index is equal to the peak of the modulating signal over the peak of the carrier signal. So EM is over here, EC, okay, is here, and I cancel away this half. Okay, in result, I actually obtain the computation of modulation index, which is Vmax minus Vmin over Vmax plus Vmin. Okay, let's quickly do an example in order to understand this modulation index discussion. Okay, for AM signal shown below, okay, so this is a typical AM signal in time domain. So again, from here, you can extract some formulas. Firstly, I know the Vmax. Second, I know my Vmin. Okay, I can also compute my modulating frequency, okay, which is 1/250 microsecond. Okay, so this is a period for the modulating signal. Okay, I also can calculate the frequency of my carrier signal, okay, which is 1/10 microsecond. Okay, so now we are ready to do this question. Okay, firstly, calculate the modulation index. Okay, by now you should know that to compute the modulation index is equals to Vmax minus Vmin over Vmax plus Vmin. So I know my Vmax is 8, my Vmin is 2, so I compute my M is equals to 0.6. Next, I need to find the equation for the modulating signal. Okay, so this is the equation for my modulating signal. The unknown, okay, they are in red. Okay, I need to find the V-bit of the modulating signal, and I also need to find the frequency of the modulating signal. So again, I'm ready to do this. This is the formula to calculate EM. So I can compute that EM is equals to 3 volt. Okay, I can also quickly calculate the frequency of the modulating signal, which is 4 kilohertz. And with this, I substitute into the equation. Okay, I actually find the equation for the modulating signal. Next, okay, I'm tasked to draw the spectrum for the AM signal. Okay, more precise is AM modulated signal. Okay, so this is how does the AM modulated signal look like in a frequency domain. Okay, this is double sideband full carrier because you see that there is still a carrier over here. So from here, you see that there are actually two unknown. One is EC, another one is FC, the frequency of the carrier. So again, I can quickly find what is EC and the frequency of the carrier. So from here, I obtain that EC is 5 volt, carrier frequency is 100 kilohertz. So I can substitute into the diagram here. So EC is equal to 5. Okay, how to find the peak value of the upper sideband? Okay, M is equal to 0.6 multiplied by this 5 divided by 2, which is 1.5. The upper sideband and lower sideband, they are symmetric. So therefore, I know that the V peak of lower sideband is also 1.5. Next, I'm ready to do the frequency. The carrier is equal to 100 kilohertz. And if you still remember, modulating is actually 4 kilohertz. So therefore, this is the frequency that I have obtained. Last but not least, on the bandwidth, okay, how to calculate the bandwidth for amplitude modulation is simply 2 times the frequency of the modulating signal, okay, which is 8 kilohertz. I can use another method. Okay, I can use the highest frequency minus the lowest frequency, which also give me exactly 8 kilohertz. With this, I'd like to stop our discussion. Please help to like and subscribe. Thank you so much.